Hi, Michael.
Hey Charles, how's it going?
It's going pretty well. How's it going with you?
It is a beautiful fall day here in Providence, Rhode Island.
Oh, that's right. It's fall when you are.
Yeah, I think that's right.
So, what we're going to do today, Michael, if you will indulge me, is we're going to talk about a different class of learning algorithms and approaches than we've been talking about before.
So now the other ones were low class. This is going to be high class.
Exactly. And we call them instance based learning, which sounds very hoity toity and highfalutin. Don't you agree?
Yeah, sure. Why not? It sounds like it maybe has good posture.
It does, in fact, have good posture.
Well, let's learn about it. I'm intrigued.
Yeah, so I think that what we're going to end up talking about today is kind of interesting. I hope, but it's sort of different. And what I'm hoping is through this discussion is that we will be able to reveal some of the unspoken assumptions that we've been making so far. Okay?
Unspoken assumptions. It sounds. Yeah. Okay. That sounds like we should get to the bottom of that.
Yes. So let's do that. So just to remind you of what we have been doing in the past, this is what was going on with all of our little supervised learning tasks. Right? We were given a bunch of training data labeled here as, XY1, XY2, XY3, dot, 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 XYZ. And we would then learn some function. So, for example, if we have a bunch of points in a plane, we might learn a line to represent them, which is what this little blue line is. And what was happening here is we take all this data, we come up with some function that represents the data, and then we would throw the data away, effectively. Right?
Okay. Yeah. So like black is the input here, and then the two blue things are what gets derived by the learning algorithm.
Right, and then in the future, when we get some new data point, let's call it x, we would pass it through this function, whatever it is, in this case, probably a line, and that would be how we would determine answers going forward.
Yeah. That's what we've been talking about.
Right, and in particular, without reference to the original data. So I want to propose an alternative, and the alternative is basically going to be to not do this. So let me give you let me tell you exactly what I mean by that. Okay, so here's what I mean concretely by not doing this thing over here anymore. So here's what I'm proposing we do now. We take all of the data, all of that training data we had, the XY1, XY2, dot, 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 XYN, and we put it in a database.
Aha.
And then next time we get some new X to look at, we just look it up in the database. And we're done. None of this fancy schmancy learning, none of this, producing an appropriate function like, WX plus B or whatever the equation of a line is. None of that fancy stuff anymore. We just stick it in a database. People have written database programs before. We look it up when we're done, period.
I feel like you've changed the paradigm.
Yes, I'm a paradigm changer. So what do you think?
It's disruptive. It's going to throw off the markets.
Yeah, it's going to change everything. So what do you think?
Well, I mean, so there's a bunch of really cool things about this idea, which is why I'm excited. So one is it doesn't forget, right? So it actually is very reliable. It's very dependable, right? So if you put in an XY pair and you ask for the X, you're going to get that Y back instead of some kind of, crackpotty smoothed version of it.
Right. So yeah, that's a good point. So if we look at this little blue line over here, you'll notice that, say, for this little X over here, we're not going to get back what we put in. So it remembers. It's like an elephant. Good.
So that's kind of cool. Another thing is that there's none of this wasted time, doing learning. It just takes the data and it's very rapidly just puts it in the database. So
Okay,
it's
so
fast.
It's fast. It's like that. I like it when you say nice things about my algorithms. Okay, so it's fast. Anything else you can think of?
Yeah, I could think of one more thing at least,
Mm-hmm.
which is that, like you, it's simple.
That's true. I am simple. I am simple and straightforward. I just need a few things to make me happy.
Bacon.
Bacon and chocolate.
Oh, nice.
Have you ever had chocolate-covered bacon?
That seems wrong.
You would think so, but it turns out it's delicious. It's like if you take fat and sugar and you put it together, somehow you like it. I'm not making this up. You can buy chocolate-covered bacon. You're unsurprised to hear in America. Okay, so we've got three good things. It remembers stuff, so none of this little noisy throwing away information. It's very fast. You just stick it in a database using your favorite database, and looking up is going to be equally as fast. And it's very simple. There's really no interesting learning going on here. So it's the perfect algorithm, and we're done.
Okay. I mean, it feels like there's more that we need to say, though.
Like what?
In particular, the way that you wrote this, f of x equals lookup of x, if I give you one of the other points in between, then it will return no such point found, which means it's really quite conservative. It's not willing to go out on a limb and say, well, I haven't seen this before, but it ought to be around here. Instead, it just says, I don't know.
So the downside of remembering is no generalization.
And I guess a similar sort of issue is that when you call it memorization, it reminds me of the issues that we saw with regard to overfitting. So it models the noise exactly. It models exactly what it was given. So it's going to be very sensitive to noise. So it's kind of a yes and no.
So that's a little scary. And it can overfit in a couple of ways, right? It could overfit by believing the data too much. That
Hmm.
is literally believing all of it. And what do you do if you have a couple, speaking of noise, what if you have, a couple of examples that are all the same? So I've got an X shows up multiple times, but each time with a different Y.
Oh, the same X. Ah, yeah. So then lookup would return two different things, and this algorithm or whatever that you've described so far wouldn't commit to either of them, and it would just say, hey, here's both.
Yeah, that seems problematic.
Okay. All right. But I feel like, you're going to tell me how to fix those things, so I wasn't too worried yet.
Yeah, well, there's got to be a nice way of fixing it. I think there's sort of a basic problem here, which is that uh, we're taking this remembering and then looking up a little too literally, right? So I stick in the data and I can get back exactly the data that I got, but I can't get back anything that I don't have. And that seems like something we might be able to overcome if we're just a little bit clever.
Mm.
So let's see if we can be a little bit clever. Okay, Michael, so let's see if we can work together to deal with this minor trifle of a problem that you've observed with my cool new algorithm, okay? So here's some data. It's a graph. You see here's a y-axis and here's an x-axis. And each of these points represents a house on this map, which I'm cleverly using in the background.
Aha.
And you'll notice that each of the dots is colored. I'm going to say that red represents really expensive houses. Blue represents moderately expensive houses, and green represents really inexpensive houses. Okay.
Okay.
So
Where is this?
where is this? Oh, this is Georgia Tech, as you can tell, because it says Georgia Tech.
Oh, I see it now.
Okay. So here's what I want you to do using machine learning. I want you to look at all of this data, and then I want you to tell me for these little black dots whether they are really expensive, moderately expensive, or inexpensive. But I want you to do it using something like the technique that we talked about before.
Okay.
So let's look at this little dot over here, which, by the way, I want to point out this little black dot here by the U.S. Post Office underneath the rightmost E over here is not a point in our database. But I think by staring at this, you might be able to come up with a reasonable guess about whether it is moderately expensive, expensive, or inexpensive.
Okay, yeah, I think this is a helpful example because now I see that it does kind of make sense, especially in this context, to think about the geometric location as actually being a really useful attribute for deciding how to label the new points. So that black point that you pointed out is in the part of a neighborhood that has a green dot in it, like the nearest dot to it. Seems like a pretty good guess as to what the value of that house might be. So I'm going to guess green.
Yes, and I think you would be right. And I like the word that you used there. You talked about its nearest neighbor. So I like that. I'm going to write that down. Neighbor. Okay. So I'm going to look at my nearest neighbor. Well, let's see if this works for another point. Let's look at another point that's near an E. Let's see the first E over here. This little black point over here. What do you think? If I looked at my nearest neighbor, what would I guess?
Yeah, this one seems really clear. It's surrounded by red. It's in the red part of town.
So you're guessing the output is then purple?
No, I'm going with red.
Yes, and I think that makes perfect sense. So this is pretty cool. I have a point that's not in my database, but I still, by looking at my nearest neighbor, can sort of figure out what the actual value should be. So there, we have solved the problem.
Yeah, it seems like a pretty good rule.
Yeah, just look at your nearest neighbor and you're done. There. So, boom. There's nothing else for you to do.
Yeah, except that you didn't do all the houses yet.
Okay, well, what did I miss?
The one in the middle,
Mm-hmm.
and I'm wondering if maybe you did that on purpose because this one has some issues.
What are its issues besides being too near 10th Street?
Well, yeah. Apart from that, it doesn't really have any very close neighbors on the map. So the closest that you get is, I don't know, maybe that red one.
Maybe.
But I'd be very wary of just using that as my guess because it's also pretty darn close to a blue point,
Yeah.
and also not so far from the green point.
That's a good point. So this whole nearest neighbor thing doesn't quite work in this case when you've got a bunch of neighbors that are saying different things and they're all kind of close to you. So any clever way we might get around this?
I would say move the black dot to
No,
no.
no,
Okay.
we're not
All right.
allowed to do that. We've tried that before.
It seems like it would be helpful.
No, there are federal laws against that sort of thing.
I was gonna say, yeah. So, all right. So short of that, maybe we just need to look at a bigger context.
Ah, that makes sense. So you're saying my little nearest neighbor thing sort of worked, but the problem was I started out with examples that were, you know, very clearly in a neighborhood, and now I'm in a place where I'm not so sure about the neighborhood. So I should look at more of my neighbors than just the closest one. Okay, so how many do you want to look at?
Well, in this case, I feel like I could draw a kind of extended city block zone and capture maybe, I don't know, 5 of the points.
Okay, let's do it. So let's find our five nearest neighbors. So let's see. This is clearly close. It's 1 over here, and I'd say this is close. I'd say this one is close. This one's close. None of the other blue ones are actually that close, and I'd say that's the next closest one. So here are my little 5 points that all seem relatively near. So what does that tell you?
Well, I mean, it feels like it suggests red is not a bad choice here. It's in a reddish part of town.
Yeah, I get that. So you think it's pretty fair thing to bet that this should be red then?
Yeah, I mean, I think if you were really asking me seriously, I would wonder about that blue point to the right of the highway and whether that had any influence.
That's pretty far away.
Yeah, it's not that far away.
Well, in Atlanta, once you cross highways, you might as well be an infinite distance away.
Well, so, okay, but that's a good point then. So I guess I was interpreting your notion of distance as being, like straight line distance on the map, but maybe that doesn't make sense for this kind of neighborhood example.
No, that's a good point. So we've been talking about distance sort of implicitly, but this notion of distance is actually quite important. So maybe distance is straight line distance, maybe it, as a crow flies, maybe it's driving distance, maybe it has to take into account the fact that when you cross highways in Atlanta, you're typically moving into a completely different universe. These sorts of things matter.
Yeah, so I could imagine, I don't know, like Google Maps distance.
Right. Or how many different paths can you get there and which is the shortest one given the traffic? There's all kinds of things like that you could do. So that's fair, that's fair. But that just says that this distance, we have to be very careful what we mean by distance, and that's okay. But let's just say for the sake of this discussion that these are the closest points by some reasonable measure of distance. So in that world, would you be happy if you had to pick a single example, a single output, a single label of red, blue, or green? Would you be happy picking red?
Yeah, I mean, not ecstatic, but okay.
That's fair. So I like this. So we went from just picking our nearest neighbor to picking our nearest neighbors. And what's a good value you think we should stick to with neighbors? We started with 1, and that clearly wasn't good. You picked, at least not in all cases, and you came up with 5. So what do you think? What if I wanted to call this algorithm something? What do you think? 5 nearest neighbors? What do you think? What should I call it?
5 seems good. I mean, I feel like that's got to be universal.
The number 5?
Yeah.
Well, it is in Atlanta, but it might not be universal in wherever it is you are.
We'll call it the Georgia Tech nearest neighbors.
That doesn't seem like an algorithm that's gonna be used very much.
Fair enough. All right, so what about we could do as many nearest neighbors as is appropriate. Well, maybe we should just make it a free parameter and call it K.
Okay, I like that. K nearest neighbors. So we'll have K nearest neighbors, and we'll pick our K neighbors. Oh, you said something fancy there, by the way. You said free parameter. I like that. We should come back to that again. So we have an algorithm, K nearest neighbors, which takes K nearest neighbors as a way of deciding how you're going to label some query point here. And we've identified 2 parameters to the algorithm so far. K, which is the number of neighbors we're going to use, and some notion of distance.
Oh, sure.
Which here we were kind of using in the sort of obvious way, but there might be other ways we might want to use distance here.
Yeah, like I could imagine if the houses had additional features like how many square footages they had.
Right, stuff like that. That would make perfect sense. So really distance, we're using distance here in a kind of an overloaded sense because this is something that's on a map. But really distance is a stand-in for similarity.
Ah, similarity, good. It's kind of stand-in for the opposite of similarity.
Well, distance is just a kind of similarity, right? But in the case of points on a map, similarity, it sort of makes sense because, as you said, when we're talking about real estate, location matters. So there, similarity really is kind of the inverse of distance. But in other ways, things like the number of bedrooms you have, whether you're on one side of the highway, the other, the school district you're in, things like that, are other things we might add as features or dimensions when we talk about similarity or distance. Okay, so I like this. So I think we have a general algorithm now, and I think it does a pretty good job of addressing the points you brought up. We no longer have to worry about overfitting as much, at least it seems that way to me, and we have a way of being a little bit more robust to this, not having an exact data point in the database. So maybe we should turn this into an algorithm.
Yeah, let's go for it.
Okay, let's do that. Okay, so what we have here, again, is pseudocode for our KNN algorithm, and I'm sort of writing it as like a function. So you're going to be given some training data D. So that's the little XY points, XY1, XY2, XY3, so on and so forth. You're given some kind of distance metric or similarity function. And this is important because this represents our domain knowledge, as I think we've already said. You get some number of neighbors that you care about, K, hence the KNN, which also, by the way, represents domain knowledge. Tells you something about how many neighbors you think you should have. And then you're given some particular new query point, and I want to output some kind of answer, some label, some value. So the KNN algorithm is remarkably simple. Given these things, you simply find a set of nearest neighbors such that they are the K closest to your query point.
Okay, I'm sort of processing this. So the data, the capital D, are those pairs, and there's a set of pairs?
Yes.
Okay. And K smallest distances. So this NN, this is a set?
Yes.
And it consists of all the elements in the data that are closest to the query point.
Yep.
And so the query point is a parameter of that. Okay, yeah, all right. I think. And then it says just return.
Yeah. So we haven't figured out what to return. So there's two separate cases we've been talking about so far. One is where we're doing classification, and one is where we're doing regression. So a question for you would be, what do you think we should do when we're doing classification? Sort of what we were doing before on the map. What would be a way of returning a proper label?
So you want a label, not like a weight on a label or something like that?
No, I want a label. You have to produce an answer. You have to commit to something, Michael.
All right. Can I commit to more than one thing?
Nope.
Okay. So I would say that a reasonable thing to do there would be, we have the Y's associated with the things in NN.
Yep.
So I would go with they should vote.
Ah, I like that. I think that's a good one. So we'll simply vote. And what does it mean to vote?
It means, let's see. So I feel like there would be a way to represent it in terms of NN, the set. Like, do you want me to write it formally?
No.
Oh. Then I would just say the closest points, whichever YI is most frequent among the closest points wins.
Yeah, right. So you want to find a vote of, basically a vote of the YIs that are part of the neighborhood set. And you take the plurality.
Ah, plurality, I see. So it's whichever one occurs the most.
Right. It's the
what
mode.
If there's ties? The mode, right.
Mm.
A la mode.
What if there are ties? That's a good point. Well, if there are ties among the output, then you're just going to have to pick one.
Okay.
And there's lots of ways you might do that. You might say, well, I'll take the one that is, say, most commonly represented in the data, period. Or I'll just randomly pick each time. Or any number of ways you can imagine doing that.
The one that's first alphabetically.
The one that's first lexicographically.
Mm.
Okay, what about in the regression case?
Okay, so in the regression case, our YIs are numbers.
Mm-hmm.
And we have the closest YIs. So we have a bunch of those numbers. And it seems like if you have a pile of numbers and have to return one, a standard thing to do would be to take the average or the mean.
Yeah. So let's just simply take the mean of the YIs. And at least there you don't have to worry about a tie.
That's right. Though I guess, we didn't really deal with the question of what happens if there's more than K smalls. Like, what if they're all exactly the same distance? All n of them are exactly the same distance. So which are the K closest?
Well, there's lots of things you could do there. I guess what I would suggest doing is take the if you have more than K that are closest because you have a bunch of ties in terms of the distance, just take all of them. Get the smallest number greater than or equal to K.
Okay.
Does that seem reasonable?
Yeah, I think that's what college rankings do.
Actually, that is what college rankings do. And then that's exactly what college rankings do. So let's do that. We know that college rankings make sense.
Yeah, they're scientifically proven to be
Used.
scary to people in colleges.
That's exactly right. So here's what we got, Michael. So all we do is we take the training data. We have some notion of similarity or distance. We have a notion of the number of neighbors that we care about. We have a query point. We find the K closest ones, breaking ties accordingly. And then we basically average in some way, in a way that makes sense for classification, a way that makes sense for regression, and we're done. It's a very simple algorithm. But some of that's because a lot of decisions are being left up to the designer. The distance metric, the number K, how you're going to break ties, exactly how you choose to implement voting, exactly how you choose to implement the mean or the average operation that you chose to do here. And you could put a bunch of different things here and you end up you could end up with completely different answers. By the way, one thing that you might do, just to give you an example of just how much range there is here, is rather than doing a simple vote by counting, you could do a vote that is, say, weighted by how far away you are. So we could have a weighted vote.
Oh.
That might help us with ties.
That could help with ties, yeah.
You could do a weighted average.
Yes. Right. So you're basically saying that the Y values that correspond to X values that are closer to the query point have more of an influence on the mean.
Which makes some sense, right?
No, I think it makes a lot of sense.
So how would you weight that, by the way? What would you do?
I'd weight it by the similarity.
Right. So, well, in this case, the similarity is we have a distance, not a similarity. So you'd have to, weight it by something like 1 over the distance.
Oh, I see. Okay. That seems like a hack.
Sure, but it's a hack that sort of makes sense.
Okay.
Okay. So anyway, simple algorithm, lots and lots of decisions to make here, all of which could, in principle, have a pretty big effect. And so in order to see that, I want to do 2 quizzes that I hope get to the heart of this and maybe give us a little bit of insight into how some of these decisions might matter on the one hand, and exactly just how simple or not simple this algorithm turns out to be. Okay, Michael, I have 2 quizzes for you, okay?
Yay.
Here's the first quiz, and here's the way it's set up. I want you to fill in the empty boxes of this table, okay?
Ooh.
Got
There's
it?
a lot of empty boxes.
There's a lot of empty boxes.
Okay, but let me make sure I understand what's going on here. So we're looking at 3 different algorithms that are learning algorithms.
Yep.
There's one neural net.
No.
Okay, one nearest neighbor, K nearest neighbor, and linear regression.
Yep.
And for each one, you want to know running time and space. And this is on n points, I assume. Yeah, what does it mean for data points to be sorted?
So let's assume that we're living in a world where all of our data points are, in R1. Okay?
Oh. Okay,
And
well, that could be sorted.
that could be sorted, and that we're going to be outputting some real number as well. So they're points on a number line. So to make things simple for you, I'm going to say that the points that you're given are already sorted.
Okay. All right. And that makes sense if it's just a scalar. So then a query point is going to come in, and it's going to be some value, and we're going to have to find nearest neighbors or do linear regression, whatever.
Right.
All right. Now that's for running time. For space, you're talking about the space of what?
How much space you're going to have to do in order to accomplish your task. How much space you're going to have to use in order to accomplish your task.
So this is kind of like the space that's representing the classifier or the regression after training.
Yes. So, and actually that question of after training is important. So you'll notice that I've divided each of these algorithms into 2 phases. There's the learning phase, how much time it takes to learn, how much space you need to learn, and then there's the query phase. When I give you some new value and you have to output an answer, what's the running time for that, and what are the space requirements for that? Okay, you got it? And I want that for each one of these 3 algorithms.
Except for one nearest neighbor, which it appears as though you filled in for me to get me started.
Right. So just to get you started and make it easy for you to know what I'm talking about big O times here, right? I'm not going to make you write out big O. Big O is implicit. So if we look at one nearest neighbor and we ask, well, what's the running time of learning? Well, it's constant, right? Because there's no learning.
I see. You just take that sorted set of data points and you just pass it along to the query.
Right. Now, you could say that, well, I'm going to take the data points and I'm going to copy them into this database, and so it's linear, but let's assume they already come in a database or some data structure that you can use, okay?
Gotcha.
Okay, so now that actually brings us to a nice little question about how much space learning takes here. And well, because you have to store those points and keep them around, the space requirements are big O of n.
Yeah, that makes sense.
Okay, good. So given that as an example, do you think your one example in your database, do you think you can use that to build up labels for all the rest of the phases of the different algorithms?
Yeah, I think so.
Okay, cool. Go for it. Okay, Michael, are you ready?
I am afraid so.
All right. Which one do you want to fill out first?
Let's just do them in order. So one nearest neighbor, you explained how the training works. We just take the sorted list and leave it there.
Mm-hmm.
And we have the classifier or the regressor itself has linear space. And now at query time, we need to find the nearest neighbor,
Mm-hmm.
which we could do by taking the query point and running through the whole list and seeing which one it's closest to. But because it's sorted, I think we ought to be able to use binary search and in log time find the closest point to the query.
That's exactly right. You should be able to do that in log-based 2 time. What if it weren't sorted?
Yeah, then like I said, I think you can just scan through the whole list and that would be linear time and that's not a big deal.
Right. Yeah, we could do it in linear time, but because I gave you a sorted list because I'm so helpful, you can do it in log in time. Okay.
That was very, very thoughtful of you.
It was. I thought it through. So what about on the space side?
All right, so the amount of space that you need to process this query is linear. We don't need to take any special set-aside space beyond a couple simple variables and the data that we're given, which we've already accounted for.
Right. So then why would it be linear if we've already accounted for it?
Did I say linear? I meant constant.
Yes. Yes, that's right. Constant. That's what you meant. That's what you said. That's what happened. Okay.
It's a good thing that this wasn't being recorded so we can verify one way or the other.
It is a good. Maybe we'll look it up in Wikipedia, and it'll say confusingly, linear is sometimes used to mean constant.
Constant. Yeah, that is pretty confusing.
Okay, what about K and N?
All right, K and N. So the training process, the learning process is exactly the same as it is for one nearest neighbor, which is to say you do nothing and you pass all the data forward to the query processor. So it's going to be 1N.
That is correct. Nice.
All right, now querying seems like it's a little more subtle. So we can find the single nearest neighbor in log n time.
Mm-hmm.
Where are we going to get the other k minus 1? So I'm pretty sure that once we find the nearest neighbor, we can kind of start doing a little spread out search from there until we found the k nearest neighbors.
Sure. So you're saying, you've got these points, they're already in a line. You find the nearest neighbor. The next nearest neighbors have to be within k of the points surrounding it. And so you could just move in kind of either direction and pick them up as you go.
Yeah, something like that.
Okay.
I mean, the way that I was thinking about it is that I think you can use the same algorithm that's used for merging lists in merge sort. But here the lists actually correspond to being to the left of the query point and being to the right of the query point. And they're both sorted in terms of their distance from the query point.
Sure. Yeah, I buy that.
So that ought to give us log n plus k.
Okay. So do we need to write the k?
I'm going to say yes, because if k is on the order of like n over 2, then it's going to dominate. If k is on the order of log n, then it's not going to dominate.
That's a good point. So, yeah, we'll do k. I will point out that if k is on the order of n over 2, you're right, it will dominate. And then really this is big O of n. But
That's
if
right.
it's on the order of log n, then it's just log n plus log n, and so it's big O of log n. But you're right. So we should probably keep the k around because we don't know its relationship to n. Okay, fair enough. Okay, what about the space requirements?
We know one bit of relationship. It's smaller than or equal to n.
That's true.
Because that would be really weird if I gave you 10 data points and asked for the 20 nearest neighbors.
This is the sort of thing you would do.
It was the sort of thing you would do, but then it would be really confusing.
No, this is the sort of thing you would do. Let's go to Wikipedia. Confusingly, 20 is sometimes mean to mean 10. Okay, so what about space?
Space. So I don't understand why it would ever need more than constant space. So we're going to zip around in that list. I mean, I guess if we do it really badly, we can use k space to kind of copy over what those possible nearest neighbors are, but we don't need to keep track of them. We can just point to them in place. So it's constant.
Okay. Yeah, that's true. In fact, because it's sorted, all you really need to know is the beginning and the ending. So that's two things. That's constant. Okay, cool. All right, good. So what about linear regression, your favorite little algorithm thing that you did when we talked about this before?
I do like linear regression. All right, so the learning in this case is what we're mapping a real number input to a real number output. And the way we're doing that is we're taking, it's probably like mx plus b sort of form.
Mm-hmm.
So we need to find the multiplier and the additive constant, which it seems like, well, so in general, doing a regression involves inverting a matrix. But in this case, I think the matrix that we're talking about is of constant size. So inverting it is constant time. I think it's as easy as basically just scanning through the list to populate that constant size matrix. So I'm going to say order n
Yep,
to process the data.
that is correct.
And there's probably a really nice algorithm for that.
Yeah, probably some kind of linear regression algorithm.
Yeah. No, I mean, like the general linear regression algorithm involves inverting a matrix
Right.
or something like it, something equivalent to it. But here, because it's all in scalar land, I think it's simpler.
Yeah, I think that's right. Okay, so what about space?
All right, so space in terms of the data that you pass forward from the learning algorithm to the regressor is just, well, mx plus b. It's just m and b, which is constant. There's the two numbers.
Right, so that's 2. 2 is like 1 for sufficiently large values of 1. So it's constant.
Yeah. All right, now at query time, you give me an x, I multiply it by m and add b. So that's constant time.
Yep.
So before, the query cost was expensive and the learning cost was cheap, and now we've kind of swapped that around.
Yeah, we have. So space would be...
Space. Oh, that you're asking me.
Yes.
Space for the query would be constant as well.
Right, exactly. So yeah, so you made a good point here. So earlier on, we had this situation where learning was fast, constant, and querying was, not as fast. It was, probably logarithmic. But in the linear regression case, learning was expensive and the querying was easy. So we swapped them around. That's exactly right. So why would you care about that? Well, let's see. I'll point out something, which is, though, even though we swapped out what was expensive in terms of time and what wasn't, you'll notice that it's only logarithmic at query time for these first two, but it's linear for the learning time in linear regression. So doesn't that mean that linear regression is always slower and worse?
Well, not really. I mean, because we don't know how many times. We only have to learn once, but we could query many, many times.
Right. Right. So I guess if we query more than, n times, for example, it'll certainly be worse overall in terms of running time.
That's right.
Okay.
Though it's interesting because, like, when I see numbers like this, my algorithm hat tells me that I should try to balance them a little bit more. Like here, it's you can make learning essentially free, and the other one you can make querying essentially free. Really, you want to split those somewhat evenly, though it's not obvious to me how you would do that. Like square root of n learning time and then square root of n query time or something like that.
Yeah, but you did say something else that was important, right? Which is that you only have to learn once.
Yeah, that's true.
So the balance, it really depends upon how often you're going to do querying and exactly what power it gives you. I mean, the trade-off is really there, don't you think?
Yeah, I guess so. I mean, so specifically in the version where you just query once,
right?
Then the balance thing could be more interesting.
Sure. Okay, cool. All right, anything else you want to observe about this? Let's see. We got the trade-off between learning versus querying. So either you do all your work up front or you put it off and do your work only when you're forced to at query time.
Yeah, I guess. Well, one thing is I want to point out that there's a nice Mr. Rogers reference in the title. That was very cool.
Thank you very much.
And the second thing is that it does strike me, in a sense, that what's going on here for the nearest neighbor algorithms is you just put off doing any work until you absolutely have to, which strikes me as kind of a procrastinatory approach.
So that's a good word that you use there, procrastinate. The words that people use in the literature are lazy. They say that these are lazy learners versus something like linear regression, which is an eager learner.
Eager.
Yes. So linear regression is eager. It wants to learn right away, and it does. But nearest neighbor algorithms are lazy. They want to put off doing any learning until they absolutely have to at query time. And so we refer to these classes lazy, and this class is eager.
I see. So I guess it's the case that if we never query it, then the lazy learner definitely comes out ahead.
Right. That makes sense.
Yeah.
It's just-in-time learning, or JIL. Or JITL, I guess, which doesn't roll off the tongue anywhere near as well. Okay, cool. So we've gotten through this quiz. Would you like to do another one?
Yeah, I just have to get this jittle off my tongue.
Okay, Michael. So here's our second quiz in a row. In the last quiz, we talked about running time and space time, but now we're going to talk about how the KNN algorithm actually works. And in particular, how different choices between distance metrics, values of K, and how you're going to put them together can give you different answers, okay? So what I have over here on the left is training data. This is a regression problem. And your training data is made up of XY pairs. X is two-dimensional, okay? So this is a function from R squared to some value in R1. Okay?
Mm-hmm.
So the first dimension represents something, and the second dimension represents something. And then there's some particular output over here. And what I want you to do is, given a query point of 4, 2, produce what the proper Y or output ought to be, given all of this training data. You with me?
Yeah.
Okay, so I want you to do it in 4 different cases. I want you to do it in the case where your distance metric is Euclidean. Okay?
The distance metric in R2?
Yes.
Oh, I see, because we're going to measure the distance between the query and the different data points. Yeah, okay,
Right. So it's Euclidean for a case of 1 nearest neighbor and 3 nearest neighbor. And I want you to take, for example, in the 3 nearest neighbor case, I want you to take their output and average them. Okay?
Okay.
Now, in the, I also want you to do the same thing, but in the case where instead of using Euclidean distance, we use Manhattan distance. But again, for both 1 nearest neighbor and 3 nearest neighbor, and in any case where we have ties, like in 3 nearest neighbor where we absolutely have to have at least 3 of these things show up, just let them average, okay? And we're doing averaging instead of straight voting because this is a regression problem.
Got it.
Okay. Any questions?
Maybe. Let's see. 3 nearest neighbor. And so if there's ties, we use the college ranking trick of including everybody who's at least as good as the K largest or K closest.
Yes, exactly.
Okay. Yeah, no, I think I could take a stab at this.
Okay, cool. Then go. All right, Michael, you ready?
Yeah.
Okay, what's the answer? Walk me through.
I will walk you through. All right, so let's do this. Let's write the Euclidean distance. Well, let's write the Manhattan distance because I don't want to take square roots in my head.
Okay.
Let's write the Manhattan distances next to the x's.
Okay.
Or the y's.
All right.
Either way.
Let's do it next to the x's. So this is the Manhattan distance, or MD, as the cool kids call it.
Is that true?
Yeah.
I thought the cool kids called it L1.
No. Have you ever heard a cool kid ever say something like L1?
Well, to me, the cool kids are the people at NIPS who know more math than I do. Yeah. Do you think any of them are going to watch this video?
Actually, I'm afraid all of them are going to watch this video.
Now I'm really afraid.
So you better get it right. Everyone's watching.
All right. Well, let me compute the Manhattan distances. So the first one, what you do is you take the 1 minus 4, and that's 3, and you take the 6 minus 2, and that's 4, and you add those two together, and you get 7, which interestingly is the same as y, but I think that's a coincidence.
Okay. So Manhattan
So
distance is 7.
Yeah, and now I'll do all the rest of them because I pre-computed them. 4, 6, 8, 4, 6. All right, so now we've got it set up so we can do 1 and 3 nearest neighbor relatively quickly. So the 1 nearest neighbor, the closest distance, is 4. But unfortunately, there are 2 points that have that, 2, 4, and 7, 1. They have outputs of 8 and 50 because they almost agree with each other. Not. And if we take the average of those two things, we get 29.
Yep. That is correct, Michael.
Great. Now, in terms of the 3 nearest neighbors, we have the 4s and the 6s. So there's 4 3 nearest neighbors.
Yep.
Somewhat awkwardly. And then we have the average of those things, which is what? 8 and 50 and 16 and 68, which gets us 35.5.
Right. Obviously. Okay. All right. So that was pretty straightforward. And those answers aren't too far off from one another. So what about the Euclidean case?
All right. So one thing to point out, I was worried about computing square roots, but it occurs to me that I actually don't have to compute square roots because that's a monotonic transformation, and we only care about the orders.
Okay.
So for Euclidean distance, or as I like to call him casually, Ed, we can just take the square differences summed up.
Okay, so this would be Ed squared.
Yes, it would be Ed squared.
Okay, Ed.
Good. So the first one, it'll be the 1 minus 4 is 3, squared is 9, and the 6 minus 2 is 4, squared is 16, and 9 plus 16 is 25. So the first one will be 25.
I noticed the square root of 25 is pretty easy to compute.
Yeah, but the other ones aren't going to be. It just so happens that we've got a Pythagorean triple on our hands.
I love those.
All right. So the remaining ones, the Ed squareds, are 8, 26, 40, 10, and 20.
None of those are easily square rootable.
Exactly. Though 40 feels like it really was trying and failed.
Yeah.
And 8 overshot, and now it's a perfect cube. So 8 is the smallest distance.
Yep.
And again, seemingly coincidentally, the y value associated with that is 8. So an 8 is our answer.
Good, and that's correct.
All right, and the 3 closest are 8, 10, and 20.
Mm-hmm.
And if we average the y values for those, that's 8, 50, and 68, which gives us an average of 42. The meaning of life, the universe, and pretty much everything.
Yes, and that is absolutely correct. So that's kind of cool that you get completely different answers depending upon what you do.
Yeah, it does seem very different, doesn't it? I mean, there's like several orders of magnitude spread here.
Well,
Maybe not orders of magnitude, but orders of doubling.
Yes, there are orders of doubling spread. Well, you know what, Michael? I actually had a specific function in mind when I did this.
Okay, let's find out which one is the right one.
Well, the function I had was y was equal to the first dimension squared plus the second dimension. So let's call those x1 and x2. And this was actually the function that I had in place. So you square the first term and you add the second one.
Okay, and so like looking at the second to last one, for example, 7 squared is 49 plus 1 is 50. Oh, that's cool.
Yeah.
It's very consistent.
Thank you. So what would be the actual answer for 4, 2?
Okay, so 4 squared is 16 plus 2 is 18, which is close to none of them.
Right. So there's a lesson here. There's several lessons here. And one lesson I don't want you to take away. So here's the lesson. So I actually had a real function here. There was no noise. It was fairly well represented. The proper answer was 18, and basically none of these are right. But the first thing I want you to notice is you get completely different answers depending upon exactly whether you do 1 versus 3, whether you use Euclidean versus Manhattan. And that's because these things make assumptions about your domain that might not be particularly relevant. And this sort of suggests that maybe this thing doesn't do very well. KNN doesn't do very well because none of these are close to 18. That seems a little sad. But I've got good news for you, Michael.
Okay.
The good news is that actually KNN tends to work really, really well, especially given its simplicity. It just doesn't in this particular case, and there's really a reason for that. And it has to do with the sort of fundamental assumptions and bias of KNN. I happen to pick an example that sort of violates some of that bias. So I think it's worthwhile to take a moment to think about what the preference bias is for KNN and to see if that can lead us to understanding why we didn't get anything close to 18 here.
Okay, that sounds useful.
Okay, so let's do that. Okay, Michael, so I want to talk a little bit about bias, and in particular the preference bias for KNN. So let me remind you what preference bias is. Preference bias is kind of our notion of why we would prefer one hypothesis over another, say other things being equal. And what that really means is it's the thing that encompasses our belief about what makes a good hypothesis. So in some of the previous examples that we've used, it was things like shorter trees, smoother functions, simpler functions, Occam's razor, those sorts of things were the ways that we expressed our preferences over various hypotheses. And KNN is no exception. It also has preference bias built in, as does every algorithm of any note. So I just wanted to go through 3 that I thought of as being indicative of this bias, and they're kind of all related to one another. So the first one is a notion of locality, right? There's this idea that near points are similar to one another. Does that make sense to you?
Yeah, that was really important and came out nicely in the real estate example, right? So that the whole idea, the whole thing that we're using to generalize from one thing to another is this notion of nearness.
Right, and exactly how that notion of nearness works out is embedded in whatever distance function we happen to be given. And so there's further bias that might come out based upon exactly the way we implement distances. So in the example we just did, Euclidean distance is making a different assumption about what nearness or similarity is compared to Manhattan distance, for example.
So is there like a perfect distance function for a given problem?
There's certainly a perfect distance function for any particular problem.
Yeah, that's what I mean. Not one that works for the universe, but one like, if I give you a problem and you can work on it all day long, can you find, is there a notion that there's a distance function that would capture things perfectly?
Well, it has to be the case for any given fixed problem that there is some distance function that minimizes, say, sum of squared errors or something like that versus some other distance function, right?
Okay,
That has to be the case. So there always has to be at least one best distance function given everything else is fixed.
that makes sense.
Right. Now, what that is, who knows? Maybe you finding it might be arbitrarily difficult because there's at least an infinite number of distance functions.
Well, yeah, I mean, I was thinking that if we're allowed to define distance functions to be anything we want, what about a distance function that said the distance between all the things that have the same answer is 0,
Mm-hmm.
and the distance between them and the ones that have different answers is, infinity or something big.
Yeah.
And then the distance function like somehow already has built in the solution to the problem because it's already put the things that have the same answers together.
Right. You could do that. I mean, of course, doing that would require again solving the original problem. But yeah.
That's
so
right.
so such a function has to exist, or well, there's always noise. What if there's noise in your data? But some such function like that has to exist. The question is finding it. But I think the real point to take there is there are some good distance functions for a problem, and there are some bad distance functions for a problem. And how you pick those is really a fundamental assumption you're making about the domain. That's why it's domain knowledge.
Yeah, that sounds right.
Okay. So locality, however it's expressed through the distance function, that is similarity, is built into KNN that we believe that near points are similar, kind of by definition. That leads actually to the second preference bias, which is this notion of smoothness, right? That we are, by choosing to average and by choosing to look at points that are similar to one another, we are expecting functions to behave smoothly. All right, so, in the 2D case, it's kind of easy to see, right? You have these sort of points, and you're basically saying, look, these 2 points should somehow be related to one another more than this point and this point. And that sort of assumes kind of smoothly changing behavior as you move from one neighborhood to another. Does that make sense?
I mean, it seems like we're defining to be pretty similar to locality.
In this case, so I'm drawing an example such that whatever we meant by locality has already been kind of expressed in the graph.
Okay.
And by picking, this is really for pedagogical reasons. You can imagine this. These are points that live in 77,000 dimensions, and it's impossible to actually visualize them, much less draw them. I could try. I mean, here's 3 dimensions, and here's the 4th dimension. And I think I'm going to get tired before I hit 77,000. But you kind of get the idea, right? That if you can imagine in your head points that are really near one another in some space, you kind of hope that they behave similarly. Right. Okay. So locality and smoothness, and I think these make sense. This is hardly the only algorithm that makes these kind of assumptions. But there is another assumption here, which is a bit more subtle, I think, which is worth spending a second talking about, which is for at least the distance functions we've looked at before, the Euclidean distance and the Manhattan distance, they all kind of looked at each of the dimensions sort of and subtracted them and squared them or didn't, or took their absolute value and added them all together. But what that means is we were treating, at least in those cases, that all the features mattered. And not only did they matter, they mattered equally. Right? So think about the last quiz I gave you, right? I said y equaled x1 squared plus x2. And you notice we got answers that were wildly off from what the actual answer was. Well, if I know that the first dimension, the first feature, is going to be squared, and the second one is not going to be squared, do you think either one of these features is more important or more important to get right?
Okay, right. Trying to think about what that might mean. So, if it's definitely the case that when you look for similar examples in the database, you want to care more about x1 because a little bit of a difference in x1 gets squared out, right? It can lead to a very large difference in the corresponding y value. Whereas in the x2s, it's not quite as crucial. If you're off a little bit more, then you're off a little bit more. It's just a linear relationship. So, yeah, it does seem like that first dimension needs to be a lot more important, I guess, when you're doing a matching than the second one.
Right. So, in fact, we probably would have gotten different. I'm not going to go through this, but we probably would have gotten different answers if in the Euclidean or the Manhattan case, we had, instead of just taking the difference between the first dimensions, we had taken that difference and squared it. And then in the case of Euclidean distance, squared it again. And then some of those things that were closer in the first dimension instead of the second dimension would have looked more similar, and we might have gotten better answers. That's probably a good exercise to go back and do for someone else.
Yeah, I was thinking of doing it right now, but yeah, probably should leave it for other people.
Well, you can do it if you want to. So did you do it, Michael?
I did.
And?
So this is kind of now a mix between the Manhattan distance and the Euclidean distance. So I'm taking the first component take the difference, square it.
Mm-hmm.
Take the second component, take the difference, absolute value it, and add those two things together.
Sure.
All right. So if I do that with one nearest neighbor, I still get that tie, but the output answer ends up being 12.
Which is better than 24.7.
And that's better than 8, which is what it was before. So the 8 has gone up to 12. And the other one, which was, I think, 35.5, comes down to 29.5, closer again to the correct answer, which is 18. So in both cases, it kind of pushed in the right direction. It was using more of the answers that were relevant and fewer of the answers that were not relevant.
Right. So there you go. So that notion of relevance, by the way, turns out to be very, very important and highlights a weakness of KNN. So this brings me to a kind of theorem or fundamental result of machine learning that is particularly relevant to KNN, but is actually relevant everywhere. Do you think it's worthwhile to mention it?
Sure, it sounds very relevant.
All right, let's do it. Okay, Michael, so this notion of having different features or different dimensions throw us off has a name, and it's called the curse of dimensionality.
Ooh, nice audio effect.
I did like that audio effect in post-production. And it refers to, well, a very particular thing. So let me just read out what it refers to. As the number of features, or equivalently dimensions, grows, that is, as we add more and more features, we go x sub 1, x sub 2, then we add x sub 3, and add more and more of these features. As those features grow, or as the number of dimensions grow, the amount of data that we need to generalize accurately also grows exponentially. Now, this is a problem, of course, because exponentially means bad in computer science land, because when things are exponential, they're effectively untenable. You sort of can't win.
I think everybody knows that, in the sense that if you look, I've done this experiment actually. If you look in the popular press, like Time Magazine or New York Times, USA Today, people will use the word exponentially sometimes to mean exponentially and sometimes to mean a lot.
Yeah, that's actually a pet peeve of mine, the whole notion
Me too.
oh, it's exponentially bigger. No, that's not meaningful. If you're saying I have one point and then I have another point, and I want to say this point is exponentially bigger than this one, that's meaningless. It's also linearly bigger than that one.
Yeah,
Exponential
again, I think
refers to a trend.
they're not talking about the mathematical relationship. They just mean a lot.
Okay, so they're wrong, and it bothers me deeply, but I'm willing to accept it for the purposes of this discussion. Okay, exponentially means bad. It means that we need more and more and more and more data as we add features and dimensions. Now, as a machine learning person, this is a real problem, right? Because what you want to do, or like sort of your instinct tells you to do, is, oh, we've got this problem, we've got a bunch of data, we're not sure what's important, so why don't we just keep adding more and more and more features? So, we've got all these sensors, and we'll just add this little bit and this little bit, and we'll keep track of GPS location, and we'll see the time of the day, and we'll just keep adding stuff, and then we'll figure out which ones are important. But the curse of dimensionality says that every time you add another one of these features, you add another dimension to your input space, you're going to need exponentially more data as you add those features in order to be able to generalize accurately. This is a very serious problem, and it sort of captures a little bit of what the difficulties are in KNN. If you have a distance function or a similarity function that assumes that everything is relevant or equally relevant or important, and some of them aren't, you're going to have to see a lot of data before you can figure that out, sort of before it washes itself away.
Yeah, that makes a lot of sense.
Yeah, it seems a little scary. So, I think you can say these words, and the words sort of make sense, but I think it helps to kind of draw a picture. And so I'm going to draw a little picture. Okay?
Yeah.
All right. Okay, Michael, so let's look at this little line segment, okay? And let's say I've got 10 little points that I could put down on this line segment, and I want them all to represent some part of this line, all right? That's kind of K nearest neighbor-y-ish. So I'll put a little X here. I'll put one here, and I'll put one here, put one here, put one here, 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 here. Is that 10? 3, 6, 9, 10. 10, okay? And let's pretend I did the right thing here, and I have them kind of uniformly distributed across the line segment. So that means each one of these points is sort of owning an equal size subsegment of this segment. Does that make sense?
Yeah, so it's representing it in the sense that that point, when you're trying to estimate values of other places on the line, it's going to default as the nearest neighbor to being that point. So there's a very small little neighborhood of the red line segment that is covered by each of the green X's.
That's exactly right. And in fact, each one of these green X's represents how much of this segment?
Each of the green X's covers 1/10.
That's exactly right. You cover 1/10. All right, Michael, so let's say that I move from a line segment now to a two-dimensional space, so a little square segment, if that's the right technical term. And I've taken my little 10 X's and I've put them down here before. Well, so here's something you'll notice. You'll notice that each one of these X's is going to still end up representing 1/10 of all of this space, but you'll also notice that the 10th that it's representing is now, really, 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 really big.
I see.
So one way of putting it is, if you think about the farthest point as opposed to the furthest point, which would be incorrect, the farthest point that this particular first X over here is representing, it's got some distance here. Over here, the farthest point from this X, the distance is very, very far away. So a question would be, how could I make it so that each of the X's I put down represents the same amount of, diameter or distance as the X's in this line segment over here? So what do you think I would have to do?
I feel like you need to fill up the square with X's.
Yeah, that's exactly right. So let's do that. So filling them up, Michael, as you suggested, you'll notice that, at least if we pretend that I drew this right, each of these X's is now going to end up being the nearest neighbor for a little square like this, and the diameter of these little squares are going to be the same as the diameter of these little line segments. Okay?
Yeah, I agree for some definition of the word, but diameter.
Yes, and for some definition if I drew them straight. Okay, so how many of these X's are there, Michael? Can you tell? You want to count?
I'm going to multiply because
Okay.
It looks like you did 10 by 10, so
I
that'll
did.
be 100.
That'll be 100. So each one now holds 100th of the space, and I went from needing 10 points to, of course, 100 points in order to cover the same amount of space.
All right, so that definitely seems like the mild rebuke of dimensionality,
Yes.
but it doesn't seem that bad.
Okay, well, what happens if I now move into 3 dimensions? So now if I want to cover the same amount of, diameter space for, sufficient definition of diameter, I'm going to have to do a bunch of copying and pasting that I'm not willing to do. So, there'll be more X's here, and, there'll be X's here, and there'll be an X here, and I'll just kind of go and fill up the space. And, I'm not going to do this, whatever. And you'll get X's everywhere. And you notice I need a lot more X's than I had before. And by the way, I'm just showing you the outside of this little cube. There are actually X's on the inside as well that you can't see. How many X's
honest,
do you think I have?
I don't think you drew any X's. You're just like scribbling on the side of the cube.
These are X's.
You were doing so well for a while and then just lost it entirely.
Well, wouldn't you lose it if you had to write 1,000 X's?
No, because I would use computers to help me. But yes, it is very frustrating to have that many X's. But in particular, in this case, we're talking about data points in a nearest neighbor method, and that does seem like a big growth from 10 to 100 to 1,000.
In fact, the growth is exponential.
Exponential.
Right. So if we went into 4 dimensions, which I'm not going to draw, then we would need not 1,000, but 10,000 points. And in 5 dimensions, we would need 100,000 points. And in 6 dimensions, we would need 1,000,000 points, and so on and so forth. So something like 10 to the d, where d is the number of dimensions.
Wow.
Right. So this is really problematic, right? If I want, in my little nearest neighbor method, to be able to say, well, I want to make sure that the neighborhood remains small, as I add dimensions, I'm going to need to grow the number of points that I have in my training set exponentially. And that's really bad. And by the way, this isn't just an issue of K and N. This is true in general. Don't think about this now as nearest neighbors in the sense of K and N, but think of it as points that are representing or covering the space. And if you want to represent the same sort of hypervolume of space as you add dimensions, you're going to have to get exponentially more points in order to do that. And coverage is necessary to do learning. So the curse of dimensionality does not just apply to K and N. It is a curse of dimensionality for ML, period.
You mean for me?
Yes. The curse of Michael Littmanality.
Okay. And that seems really problematic because it's very natural to just keep throwing dimensions into a machine learning problem. Like, it's having trouble learning. Let me give it a few more dimensions so to give it hints. But really what you're doing is just giving it a larger and larger volume to fill.
Yeah, and it can't fill it unless you give it more and more data. So you're better off giving more data than you are giving more dimensions.
Zoinks.
Mm-hmm. There's an entire series of lessons that we will get to eventually that deals with this issue.
The issue of
Dimensionality.
finding the right dimensionality?
Yeah.
That would be a useful thing.
It would, but it's far off in the future. It's like infinitely far in the future. So we'll worry about that in a few weeks.
Okay.
Okay. All right. So there you go, Michael. Curse of dimensionality is real, and it's a real problem.
Where did that term come from? It's a cool term.
I think it came from, what's his name? Bellman.
Oh, Bellman, like the dynamic programming guy.
Yeah, the dynamic programming guy. The Bellman of Bellman equation guy.
Which we haven't gotten to yet in the course.
Which we haven't gotten to in the course, but we will get to in the course because it's central. So it looks like actually Bellman's central to a lot of things.
Wow.
Sometimes he gives us equations that helps us, but sometimes he gives us curses.
Curses, Bellman. Foiled again.
Okay, Michael, so we talked a little bit about the curse of dimensionality, but I think it's worthwhile to talk about some other stuff that comes up. We've been sort of skirting around this and bring it up in various ways throughout our discussion so far. But I think it's worthwhile kind of writing them all down on a slide and trying to think through them for a little bit. So the other stuff that comes up in KNN mainly comes up in these sort of assumptions we make about parameters to the algorithm. So the one we've talked about probably the most is our distance metric. Our distance between some x and the query point q. And we've explored a couple. We looked at Euclidean, and we looked at Manhattan, and we even looked at weighted versions of those. And this really matters. So I've said this before, but I really think it bears repeating, that your choice of distance function really matters. If you pick the wrong kind of distance function, you're just going to get very poor behavior.
So I have a question about these distance functions. So you mentioned Euclidean and Manhattan. Are there other distance functions that the students should know, like things that might come up, or things that they should think of first if they have a particular kind of data?
Yeah, there's a ton of them. I think. Well, first off, it's probably worth pointing out that this notion of weighted distance is one way to deal with the curse of dimensionality. You can weight different dimensions differently, and that would be one. And you might come up with sort of automatic ways of doing that. That's sort of worth mentioning. But you'll notice that both Euclidean and Manhattan distance, at least as we've talked about them, are really useful for things like regression. They're kind of assuming that you have numbers and that subtraction sort of makes sense. But there are other functions other distance functions you might do if you're dealing with cases like, I don't know, discrete data, right? Where instead of it all being numbers, it's colors or something like that, right? So your distance might be mismatches, for example, or it might be a mixture of those. In fact, one of the nice things about KNN is that we've been talking about it with points because it's sort of easy to think about it that way. But this distance function is just a black box. You can take arbitrary things and try to decide how similar they are based on whatever you know about the domain, and that could be very useful. So you could talk about images, right, where you take pictures of people, and rather than doing something like a pixel by pixel comparison, you try to line up their eyes and look at their mouths and try to see if they're the same shape, things like that, that might be more complicated and perhaps even arbitrarily computational to determine notions of similarity. So really this idea of distance and similarity tells you a lot about your domain and what you believe about it. Another thing that's worth pushing on a little bit is how you pick K. Well, there's no good way to pick K. You just have to know something about it. But I want to think about a particular case. Well, what if we end up in a world where K equals N?
Well, that would be silly.
Why would it be silly?
Well, so if K equals N, then what you're doing is you're taking, so in the case of regression, for example, you're taking all of the data points and averaging the Y values together, basically ignoring the query. So you end up with a constant function.
But that's only if you do a simple average. What if you do a weighted average?
A weighted average. So the points that are near the query are going to get more weight in the average. So that actually will be different. Even though K equals N, it will be different depending on where you actually put your query down.
Exactly. That's exactly right. So, for example, if I have a little bunch of points like this, say, where you notice it kind of looks like I have two different lines here, if I could pick a query point way over here, all of these points are going to influence me as opposed to these points. And so I'm going to end up estimating with something that looks more like this, because these points over here won't have much to say. But if I have a query point that's way over here somewhere, these points are going to matter, and I'm going to end up looking at something that looks a little bit more like this than like that. Now, I'm drawing these as lines. They won't exactly look like lines because these points will have some influence. They'll be more curvy than that. But the point is that near the place where we want to do the query, it'll look to be more strongly influenced by these points over here or these points over here, depending upon where you are.
Well, that gives me an idea.
Oh, what kind of idea does it give you?
Well, what about instead of just taking a weighted average, what about using the distance metrics to pick up some of the points and then do a different regression on that subset of points?
Right, I like that. So we can replace this whole notion of average with a more kind of regression-y thing.
So it actually, instead of using the same value for the whole patch, actually still continues to use the input values.
Yeah, so in fact, if average is just a special case of a kind of regression, right? Right? So this actually has a name, believe it or not. It's actually called locally weighted regression. Yeah, so this actually works pretty well. And in place of this sort of averaging function, you can do just about anything you want to. You could throw in a decision tree. You could throw in a neural network. You could throw in lines, do linear regression. You can do almost anything that you can imagine doing.
Neat.
Yeah, and that works out very well. And again, it gives you a little bit of power. So here's something that I don't think is very obvious until it's pointed out to you, which is this notion of replacing average with a more general regression or even classification function actually allows you to do something more powerful than it seems. So let's imagine that we were going to do locally weighted regression and we were going to do, in fact, linear regression. So what would locally weighted linear regression look like? Well, if we go back to this example over here on the left, basically you take all the points that are nearby and you try to fit a line to it. And so you would end up with stuff that looked pretty much like this. While you're over here, you would get a line like this, but while you're over here, you would get a line like this, and somewhere in the middle, you would get lines that started to look like this, and you would end up with something that kind of ended up looking a lot like a curve. So that's kind of cool because you notice that we start with a hypothesis space of lines in this locally weighted linear regression, but then we end up actually being able to represent a hypothesis space that is strictly bigger than the set of lines. Right? So we can use a very simple kind of hypothesis space, but by using this locally weighted regression, we end up with a more complicated space that is complicated, that's made more complicated depending upon the complications that are represented by your data points. So this results, this sort of reveals another bit of power with KNN, which is it allows you to take local information and build functions or build concepts around the local things that are similar to you. And that allows you to make arbitrarily complicated functions.
Neat.
At least in principle. Okay, cool. All right, so you got all that?
I think so, yeah.
Okay, cool. So then I think we should wrap up.
Nice.
Nice. Okay, Michael, so I think with that little bit of discussion, I feel like we're done.
Cool. All right. Well, it's been nice talking to you. I hope the course went well. And oh, you mean just for this lesson?
Yeah, just for this lesson.
All right.
So
well, let's wrap up this lesson then.
Yeah, let's see. What have we learned? So remind me, Michael, what have we learned?
Well, we were talking about instance-based learning.
That's true. That's the first thing we learned. You'll notice, by the way, I never actually told you why it was called instance-based learning.
Charles, why is it called instance-based learning?
I don't know, but I'm willing to guess that it has to do with the fact that we look at the exact instances that we have, and we base our learning on that.
All right, and we brought it up by starting off thinking about eager and lazy learning.
Right. What is the difference, Michael?
I will tell you when I need to tell you.
That's exactly right.
So lazy learning is about putting off the work until it's actually needed. Eager is about as soon as the problem is posed, solve it, and then if you're lucky, then the answer will eventually come in handy.
Exactly right. Okay. What else?
So as a concrete example of a lazy learner, we talked about K nearest neighbors, or KNN.
KNN. Yeah. And this whole notion of nearest neighbor is, in fact, one way of talking about similarity functions.
Right. And the similarity functions play a really central role in all of this.
Right. Similarity. We talked about it as if they were distance functions, but distance is just another way of talking about a similarity. So this is actually a key thing. KNN was a specific algorithm we used, and we talked about various versions of it. And the nearest neighbor part really got us to think a little bit about similarity and distance and what all that means. A really important thing here is, I think, that similarity is just another way of capturing domain knowledge. And K and KNN is another way of capturing domain knowledge. And that if we saw through the quizzes and through some of our discussion that this is actually very, very important, that domain knowledge matters.
Now, we also talked about KNN in the context of both regression and classification. Ah, I see what you did there. Knowledge. It's got KNN in it.
Okay, so yeah, so classification and regression are different things, but KNN can handle both of them. And at the end of the day, that's all stuck in our notion of similarity and our notion of averaging, which we kind of took as an overall term for a bunch of different things you might do, which some people might find confusing, but I think that other people would really kind of understand what we mean.
I'm very tempted to take that out of Wikipedia, but that would just be rude.
It would be rude. Anything else? We learned one big thing.
We looked at how to compose various different learning algorithms together. For example, in the context of locally weighted linear regression, we used this instance-based idea along with linear regression to get something that was both sort of locally smooth but globally bumpy.
Right. So I'm going to just say locally weighted regression, where we can do any kind of regression we might want to. I'm just going to call that $X. So stick in your favorite value.
Let's see, what else? Oh, a really big thing was Bellman's curse of dimensionality.
Yes.
And the idea there was that the more features that you include, the more data that you need to fill up that space.
Yep. It's exponential.
And in fact, I decided to go and play with this a little bit. So that example that you were doing before where the y equals x1 squared plus x2, when I gave it, well, as we saw in the example, we gave it like 10 or 12 examples and it did really badly.
Yep.
So it continued to do somewhat badly until I got to about 100,000. And then it was actually doing really well. But that seems like an awful lot of examples for what is otherwise a very simple problem.
Right. Well, if you think about it, the amount of data you have to see to determine the relative relevance of the two different dimensions is quite a bit in that particular kind of function. Yeah, and that's a lot of space to cover all possible real values across a potentially infinite space.
Yeah, I guess that's true.
Yeah. So the curse of dimensionality is real, and we just sort of can't get around it. Although, as I mentioned earlier, we will see in the second part of the course ways that people try to get around the curse of dimensionality.
Aha.
Okay.
Or at least blunt it, right?
Yeah, or at least blunt, because you can't actually get around the curse of dimensionality. You can only deal with it.
There is no free lunch.
There is no free lunch. In fact, that's a theorem. Isn't that a theorem?
Yeah, I think so.
What's the theorem?
No free lunch. That any learning algorithm that you create is going to have the property that if you average over all possible instances, it's not doing any different than random.
Right. And another way of thinking about that, a practical way of thinking about that is, if I don't know anything about the data that I'm going to have to learn over, then it doesn't really matter what I do because there's all possible kind of data sets. However, if I have domain knowledge, I can use that to choose the best learning algorithm for the problems that I'm going to encounter.
So does that mean that all of machine learning really comes down to you have to already know what you need to solve the problem to apply these techniques to solve the problem?
No, but you have to know a little bit about your problem in order to decide what to do. And in fact, you can make the argument that this entire class is about exposing the students to a wide range of techniques and giving them enough practice so that they can do a pretty good job of telling, given a problem, would it be better to use this kind of technique or this kind of technique? Is KNN a sort of better way of approaching it? Decision tree is a better way of approaching it. This is a lot of what this class is about, is helping them to get enough domain knowledge, or enough knowledge anyway, so that they can apply it to particular domains.
Cool. All right. Well, that seems like a plenty useful lesson.
Yes, it's a very hopeful note to end on. So let's end on that.
All right. See you next time.
All right. Bye, Michael.